I won't take the time to write it down, but you look in the paper of Kontsevich and Zagier. At the very beginning, there's an informal definition of what an exponential period was. And at the end, there's an informal definition what an exponential, right at the beginning, it's an informal definition of a period. And at the end is an informal definition of an exponential period. And so just philosophically, I'm trying to, rather than just pull out exponential motives and motives out of the air, to say something about how they might arise from periods. That seems more plausible, even though it's lacking in all kinds of details. So, Kontsevich and Zagier, section 4.3, an exponential, so you guys can look it up. You may remember the definition of a period. An exponential period is an absolutely convergent integral of the product of an algebraic function with the exponent of an algebraic function over a real semi-algebraic set in which all the polynomials enter into its definition, that is to say the domain of the integral, have algebraic coefficients. So it differs from his informal definition simply of a period by A, allowing algebraic functions with algebraic, just algebraic functions instead of rational functions with rational coefficients, generalization, but perhaps more relevantly, not just the integral of such a thing, but the integral of an algebraic function with the exponent of an algebraic function, exponents, and hence the point, a very good reference. So very good reference. These guys write well, in my opinion, even though they're just, I don't know whether they're just starting off, but the reference is Fressan, and Josen, exponential periods. No, exponential motives, excuse me. That's a book, apparently. I guess apparently he's come here and spoken, or no, I've spoken to our seminar online. Is that right? He spoke online to our seminar. It's like 300 pages, but pretty well written. I mean, there's gaps in it. I hope the book, when they publish it, they won't have these gaps in it. But it's very well written. They do explain themselves better than most people. I'll quote that a little bit. Okay, so I described examples of periods. Examples of exponential periods are, if one goes down a list, for example, in a couple of those books that I mentioned before by Yves Andre has a book, and there's another book on Nori motives, both of which are very long, and they're, I think, just regular periods. I don't think they talk about exponential periods, and I think they're just basically periods attached to, I'm not sure, but I think that a lot of it is periods attached to mixed Tate motives. But anyway, there's a huge collection of them, but there are some obvious gaps. And examples of exponential periods that are not ordinary periods, periods in the sense we talked about last week. The most obvious one is the number e. It's not a period. More generally, e to the alpha algebraic. Euler's constant. People wondered about this. It must be rather exotic. Euler's constant, gamma, the limit as n goes to infinity, log n minus the sum k goes from 1 to n, 1 over k. The harmonic series which diverges, the partial harmonic series which diverges, and the number log n, of course, to the base e, which diverges, but the difference is Euler's constant in the limit. Something else that's worth mentioning, I'm again no expert in this thing. It would be just fun to spend a few months looking at these things because they're very pretty and they're very nice, but periods and, but in any case, values of Bessel functions. At regular, now I'm not sure about whether this is, whether it would be all, that you have to take them at rational arguments. I don't know whether it's all rational arguments or most, but anyway, we won't be precise, at rational arguments. Okay, now that's relevant. That's particularly relevant because Bessel functions are solutions of linear ODEs. So when I took second year analysis or second year differential equations course, we did something called Frobenius's method, where you take second order linear differential equations with variable coefficients, unlike the ones with constant coefficients when you can write down the solution, and learned how to express their solutions as power series, except you got to make the constant term 1, and then that could introduce some poles in the coefficients of the other terms. The highest term is 1. Well, did I say the constant term? No, the highest term has to be 1, so that, you know, you got rational functions of the other terms, but they might have poles. But if the poles have a particularly nice property called the indicial equation, I think it's called, you can actually solve those as well by infinite. They're not quite power series. I think they're multiplied by an exponential, but then as a power series which converges. And then, but if you have ones whose do not satisfy this equation, that's Bessel functions. These are solutions of linear differential equations. It's if the singularities of the first order differential equation satisfy Frobenius's equation, the indicial equation. Yes, indicial equation and Frobenius's method. Yeah, then as I say, you get a convergent power series. Those are called regular singularities. If they don't, they're called irregular singularities. Irregular singularities mean you can write an infinite series for the solutions of these equations around any given point. But critical difference, this was pointed out to me by Marco, critical difference, it's an asymptotic formula. it's not a convergent power series. And I don't even mean convergent power series on the whole line, just in any interval. It's not that. It's an asymptotic formula. It took me years to really truly understand the difference between an asymptotic series approximating a given function and a convergent power series, say in a neighborhood of the point of the center. One converges and actually equals the function. The other approaches the function better and better the longer you go out in the series. And the two have rather different consequences. In any case, these things are solutions of ODEs with irregular singularity. So if you look back in some of the papers that are published on well, they don't even talk about exponential motives, a lot of them, but on Bailenson conjectures and other things, there's all kinds of papers, Bloch and Hainaut and other people, Katz, with irregular singularities. This arose, the first person to have looked at this apparently was these kind of differential equations. I'm going to write down a contradiction here. C, the unavailable. It seems to be unavailable. 1976 letter. I haven't read it. From Deline to Malgrange. So it seems to be unavailable, but there, yes.
Published as a correspondence, like irregular singularities between Deline and Malgrange.
Oh, is it? Oh, it's a book, is it?
I thought they compiled it and got it together.
Oh, okay. Well, let us know. Let us know next week. Yeah, I did a little bit of a search a couple of days ago on what is it called, Math Forum, and they said it was unavailable. But in any case, there's a report. Deline won the Abel Prize, and I think it was Illuzy that wrote a report on the work of Deline. It's not a long report, but there is a section on Deline's ideas on irregular singularities, which I haven't read, but which I'm sure is interesting. And I'll just say, as opposed, this business of Bessel functions, this is in contrast to the rational values of hypergeometric functions. At rational arguments. And that's, they come from whose differential equation has regular singularities, at least at the finite places. You could also try to expand them around infinity, and I don't know whether the hypergeometric function has irregular singularities around that, but in any case, hypergeometric functions, special values of those are ordinary periods, whereas that's not true for Bessel functions. And this relation to differential equations seems to be quite important and central to the question. Okay, anyway, so can you use, so we sort of did an informal discussion of Grothendieck's reasoning around periods to lead to the conjectural construction of motives. So can you use Grothendieck's reasoning to get exponential motives. They do exist conjecturally, and people, well, cats and people study them, but they're not nearly as widely studied as ordinary motives. But to get exponential motives from exponential periods. Question. And there's a problem. We went through a little bit, very superficially, we went through Grothendieck's reasoning and saw that periods resulted from a comparison of de Rham cohomology with Betti cohomology. So can we do that here? Well, no, we've already used it, and it gives, I suppose you could probably consider changing the domain, but no, we've already used it. Remember, we used the comparison of the two cohomologies on an algebraic variety, possibly singular, but on an algebraic variety. So that's what we want to do to get exponential motives, but we've already used these cohomology groups, the ones that we would compare. So they're not available to us. They're not going to give us anything new. We've already used. Comparison of H de Rham and H star de Rham and H star Betti to construct ordinary motives. The comparison of these two things lead to periods. They lead to a more a systematic description of periods, which for ordinary periods, which Kontsevich and Zagier do a reasonable job of convincing us. It's not an airtight proof, but convincing us that the general periods that they define can be put into this framework of comparison of these two cohomologies on algebraic varieties. So to construct ordinary motives. Anyway, that's closed to us if we want to construct something new, but there is a solution. It's very clearly explained right at the beginning, and that's all I'm doing from this volume, like page 1 or page 2 or 3, section 1.1. They do it in, I guess, greater detail later in the article, but it's very nicely described at the beginning. And the solution is you do a comparison of two new kinds of cohomology, Betti and de Rham. Different kinds of cohomology. And what are they? Some people here perhaps are more familiar with them than me, but what you do is you don't just start with a variety, which is the way X, the way we started the sort of comparison that leads to ordinary periods and eventually ordinary motives. We look at a variety, what is called a variety with potential. And what that is a pair XF. Well, I'll just say in like one sentence what this is, and then I'll just have a very brief description of what's happening. So you start with what's called a variety with potential. That gives then what is called rapid decay, Betti homology, and Betti cohomology. Betti homology, let's say H star rapid decrease. I won't put the Betty in there, but it's Betty homology. So I guess I better have it like this. Betty homology with the rapid decrease up there. XF. And Betty cohomology, which would be the dual of this, of rapid decrease, H upper star, rapid decrease of X and F. These are going to be taken with Q coefficients, and DRAM, rapid decrease. The phrase rapid decrease is also attached to DRAM, but there's no room to put it, so we'll DRAM cohomology, H star DR. So the point is that these are cohomology groups, not just attached to X, but attached to X and this function, a potential. So let's do a very brief description. So suppose, well, first of all, talk about it over in algebraically over the complex numbers. So suppose that X is a variety over the complex numbers. But we've got a second ingredient, F. So suppose that F from X to C is a regular function, an algebraic function. And then given that, what one does is to define okay, one defines the Betty homology of rapid decrease at X and F. This is, the relevance of this is the fact that F is supposed, the real part of S, that F could get very large. You want to consider the definitions attached to this when F gets very large at infinity. If F is a constant function, one would get back the ordinary cohomologies that we used before. So the definition of this is the limit as R goes to infinity of ordinary, but it's relative Betty cohomology of the complex variety XC. And with respect to a sub, so this is to be regarded as a topological space but it's relative to a subspace. I've forgotten all about relative cohomology. I learned it in fourth year undergraduate, right here, not at the fields, but in the department, and I have forgotten much of it because I've never used it. But so I'm afraid I don't feel my intuition on this is very good, but it's relative cohomology of one space relative to a topological subspace. Relative Betty cohomology with two coefficients. So we have to say what this is. SR, that its inverse image gives you a subvariety of X of C, or at least a subspace, topological subspace. This is the set of complex numbers such that the real part of Z is greater than or equal to r. Okay, so it's a right half plane. Okay, so it's the inverse image of that, which gives you this piece here for which you're taking relative homology. And I guess when you take a limit of these things, they'd be relative to inclusions. So taken relative to inclusions. F to the minus 1 of SR is contained in F to the minus 1 of SR prime here is contained in this SR if R prime is greater than or equal to R. So the subspace here that limits this gets smaller and smaller as R goes to infinity. And so, the change that happens with that is you get the difference between the cohomology and the relative cohomology gets less. But in any case, this direct limit works, and so one defines. So that's what this is. That's the this is the rapid decay. It's of course relative to F. I guess it changes radically. Yes, it certainly changes severely with changes of F, but it's called the rapid decay Betti homology. And cohomology. HRD star XF defined simply as H lower star, rapid decrease XF star. So these are the things that take the place of the homology. If F is constant, not equal to 0, F to the minus 1 of SR is empty for large R. And then the rapid decay Betti cohomology is ordinary Betti cohomology. As rational coefficients. So this is all run by us very quickly in the early pages of that article. I just copied the book today and had trouble stapling it together because it's very long, so I haven't really browsed much in the inside of it, but I imagine these things are done in greater detail in the inside of the book. And for the Durham cohomology, for Durham analog of this, suppose, at least at first, you have to talk about differential forms and Stokes' theorem and things of that nature. You really want a manifold. So suppose, at least initially, that X is smooth and defined, like we had before, defined over a number field, a field f, together with an embedding in the complex numbers. And then what you do is you take ordinary de Rham cohomology, with one significant change. You change the differential. Again, I haven't been through this, but I guess if one goes through this and kind of looks at examples, one sees that that hits the nail on the head. It really does what you want to do. So de Rham cohomology, but with the differential. D omega x to the p to omega x to the p plus 1. These, of course, are differential forms. But it's replaced by df omega. There's an f that goes into what you replace the differential by, and it's simply defined to be d omega minus the differential of f wedged with omega. This would be omega in omega a p form, any p form. And the theory works. This must be quite nicely contrived so that the theory works out. D squared would be 0. This df squared would be 0. And so this is called you could call it the de Rham cohomology of rapid decrease, but I think they just call it the de Rham cohomology not of x, but of the pair xf. So, namely, and so you would write it as h star de Rham x f. It is related to, just to say something, I mean, I'm just going, this is a remark that they make. So say I'm just copying what they say, but it all seems pretty plausible. Good writers, when they just make remarks, the reader tends to sort of feel that it's plausible and gets the idea, some portion of the idea. And I'll just say that this is related. So it's related to an integrable connection. A definition of which I've seen many times, but I would have to go back and review it because I haven't used it recently. An integrable connection defined by this operator on x. So any discussion, wider discussion of these things, de Rham and Betti, is done on maybe varieties over the complex numbers rather than over the integers. And I won't try to say this, but there is in descriptions of these things, it's the beginnings of the geometric Langlands program and lots of other things. It's also in the first of the two long papers of Francis Brown, where he talks about attaching periods to Feynman integrals. So you have it all comes from a comparison of de Rham cohomology with Betti cohomology attached to an integrable connection on its and the integrable connection is defined as a solution of a differential equation, and the correspondence between Betti and de Rham cohomology in that wider setting, that is to say, where they're not just over, well, where they depend on further other variables. It's called the Riemann-Hilbert correspondence. We won't talk about that. But the point is, in this case, as opposed to the case that people tend to work with, and in particular, the case that Francis Brown, he described this right at the very beginning. But he wasn't talking about varieties over Q or over F, but rather over several variables, over several, say, complex variables. And he worked with a situation where the connection, so that comes with a connection. He actually explains that pretty well, Francis Brown, in 1 or 2 pages at the very beginning of his first long article. And but he takes a situation where the integrable connection has regular singularities. And what's happening here is this is an integrable connection df on x with an irregular, so it's just it's a return to the theme above, an irregular singularity. All of this would have to be defined in many variables at infinity. Deligne, I think in around 1970, wrote a book on differential equations in many variables with regular singularities. And I assume that his letter to Malgrange was an extension of that, of his book, to the case of differential equations in many variables with irregular singularities. All right, so all of that, with that set up, I'm going to, I may go a couple of minutes over. I want to just introduce sort of the thing we sort of been looking forward to. So with all of that, so there's then a comparison isomorphism, like what was the case for ordinary periods. Let x and f, the pair, be a smooth variety. So we'll, for this purpose, we'll take it to be smooth variety with potential. And I want them both to be, what we had been doing up until here, we hadn't asked for anything to be defined over a number field, I think, but both, so the pair is to be a smooth variety with potential defined over a number field. A number field. Then there exists a canonical isomorphism. So this, we will recognize this from what we were talking about before. But now we're talking about it in the exponential periods case. So there is okay, so there is a canonical isomorphism from, so if you're talking about the field F, then we could take H duram star X F. We can consider that to be defined over F. And you do just what we did before. You take the tensor product over F, thanks to Walid and my correction, tensored over F with C. And the assertion is that that's, as complex vector spaces, that's canonically isomorphic to the rapid decrease cohomology of X and F, but that's over Q. I don't need to put Q in the notation. And so you would take the tensor product over Q with C. Or equivalently, they observe if one prefers a perfect pairing. You could either take this as an isomorphism between these two cohomology groups, or you could regard it as a bilinear pairing over the complex numbers of a homology group. Well, this group's always cohomology, but with the Betty homology there, a perfect pairing. Between H star duram of X and F. That's over the complex numbers. Let's just put it this way, a perfect pairing between this and this, H star rapid decrease of Betty cohomology, but this thing is a pairing over C. And as we noted before, it's a matrix. If you choose bases over the relevant fields F and Q, it's a matrix, but the entries of the matrix are complex numbers. And those are what are going to be exponential periods. So if this seems a bit murky, it's explained with not too many details in FJ, just section 1.1. It's under the this is under the assumption that X is smooth. We really want this to be something that gives us exponential mixed motives. For that, you'd need non-smooth and maybe singular varieties, and non-smooth singular varieties, but that is later removed. Much later in the book, section 7.1, using, I quote, standard homological algebra. This is what's quoted at the beginning, the introduction that I'm following. Okay. leave that there. We've got that up there. All right, before I go on, I'm going to remarks. I'm not going to call them remarks. I have two remarks, but I'm not going to call them remarks. I'm going to call them teasers. Not a technical, not in any kind of like tensors or anything like that. Just possibilities, possibilities. One, C Fj, example 114, and the accompanying diagram. The diagram figure 111 looks related. It seems related. So Waleed can perhaps comment on this. I learned such things, such as I've actually learned them from Waleed and Marco, but this seems related to the diagrams that arise, studies of sort of the ultimate goal, in some sense, of particle physics, as I understand it, of Feynman, not diagrams, but Feynman path integrals. In physics. So they draw, I mean, people, I believe, like Seubelman and Kontsevich and Seubelman, draw diagrams that look for these other things, these really dreaming dreams of getting Feynman path integrals as some kind of convergent, mathematically sound object. But the diagrams they draw look similar to this. This diagram attached to a particular example of exponential motives. Secondly, now I don't know whether you guys, Waleed, have sort of thought of it in this term, but and I may be completely off the mark, but the potential, they call it the potential F, looks something like it looks like something to be added to the free particle Lagrangian. So in this business, as I understand it, when quantum field theory, their starting point is a Lagrangian, a function that somehow from which the equations arise. So the free particle Lagrangian, and that as I understand it, it pertains to the kinetic or quadratic terms only. The first terms in a typical Lagrangian to get, so a general Lagrangian would be these quadratic terms plus a potential. well, I got an F there that's called a potential, to get a general Lagrangian. For interacting terms. So you can ignore this if you're not interested in the physics, and may not be correct, but Marco has told me that the asymptotic series obtained from adding up periods in Feynman diagrams over an infinite collection of such things is an exact formula, not an asymptotic formula, but an exact formula in a very special case, namely when you have terms that don't interact with each other, particles that don't interact with each other, which is rarely the case. If you have particles that interact with each other, then there are higher terms, higher than quadratic terms, coming from what is described as a potential in the Lagrangian. And I guess, as I understand it, the hope, dream, is that if you use exponential motives to construct Lagrangians, excuse me, if you want to, I mean, in the real situation, you have a Lagrangian that has interacting terms, and that would be the kinetic terms that don't interact with each other plus a potential. And so I just wonder whether this function f that you put in, that this is the essence of defining exponential motives, is related to that. If that were so, the dream would be to have have Feynman diagrams. That's not as much as this, but to have Feynman diagrams which whose if you took exponential motives in take an infinite sum of exponential motives according to this business here, whether that would give something that is not just an asymptotic formula, that would be an approximation for what happens in the free particle case, but rather an actual formula in the more complicated situation of a more general Lagrangian. Does that make any sense? Or have you guys talked about that? Or is it, does the potential here for exponential motives, is it related to?
I think, yeah, maybe it's a finite dimensional version of the infinite dimensional thing that they want to do.
The infinite dimensional thing is of course, the Feynman path integrals. Yes, yes. So this would fix up the Feynman diagrams and how you compute the numbers from those in terms of the motives given by the integrals in Feynman integrals. Is that, yeah.
It does do this finite dimensional version first.
And he puts a Q, and is it the Q that comes from exponential motives? Because that would tie the two.
Same Q for multi-theories, and he sets up the
Oh, great, great.
decay and the histogram like this, and then he has a for the exponential integral this f. So I think it's both the kinetic and it's a full Lagrangian.
Yes.
That's right.
Yes. Oh, that's great. That's great. So this that's great. That's very, very encouraging. So if exponential motives are then the things that might correct for this age-old problem with even just talking about Feynman diagrams that don't tell you anything about, say, the standard model, their approximation works very well, as I understand it, for quantum electrodynamics, which is very close to the free particle theory. The functions, the quantities that go into it are small enough that it's very close to the free particle, and so you get a good formula. That's still an asymptotic formula, but one which is very okay. So with your indulgence, I'm going to go. Do you mind if I go a little bit over? I'll just I'll just take 10 minutes. With the comparison isomorphism, okay, so given that, if we have that in our cache, then one could imagine applying growth and Deeks reasoning, as we tried to do in the regular periods case, to construct, well, first of all, exponential periods. From, say, that period matrix. But the point is to construct exponential periods, but then leading, the point is you construct those things, but then leading to exponential motives. Okay, so I think that people often write mote f for ordinary motives, category of ordinary motives. So let's put a tilde on top of it for exponential motives. And then to the existence of an exponential mixed motivic. Let's be greedy, an exponential mixed motivic Galois group. And so let's write that as GF. We've been writing GF for the putative motivic Galois group. So we'll write GF tilde for the mixed motivic Galois group. I guess we'd write that for the pure motivic Galois group. And then we could write GF tilde plus. We have written a plus before for the larger full motivic Galois group, not just the pure motivic Galois group. So that would be GF tilde, semi-direct product of NF tilde, which we've talked about already. So this hasn't really been talked about too much. I think it's talked about in detail in Fresson and Josen, but others don't seem to have talked about it very much. But if so, what is it? In explicit terms, Fresson and Josen talk about it as a group with a nice pro-algebraic group with I'm not sure quite how they characterize it, but as a group with certain properties, but given only by abstract axioms. What we would like, we have a description. We have a concrete description of the motivic Galois group. It's in terms of the automorphic Galois group. Well, you'd have to try to start with an exponential automorphic. Galois group. So that would be, we've been writing LF for the conjectural, I would say explicit, explicit automorphic Galois group. Let me write L tilde for the larger thing, and it should be, I assume it should be a covering of L of F. So that's what we're looking for. So I'm just going to say a few words about what one could imagine it being. And I really do think it has to be what I'm describing. I just think there's nothing else that it could be. And this thing is calling for an interpretation. Steady, lads, steady. Easy, steady on, steady on. What are they doing? Oh, it's just some, they're not clowning around. No, it's just some, what is it? Well, just a few words today, and I'll try to, if I can spend the next 4 days thinking further about this, say more about it. But what is it? Consider the group. G equal SL2. Algebraic group SL2 over Q. It's simple. But what is particularly relevant to this discussion, it's also simply connected. And what that means, algebraic groups terms, it means that GC is simply connected. But GR, think of the Iwasawa decomposition for GR. That's SL2R. Okay, so it's an it's a unipotent upper triangular matrix. So it's a diagonal matrix of entries consisting of positive numbers. Let's write it as AGR. So that's the multiplicative group of positive real numbers. It is a group NGR. That's the group of upper triangular nilpotent matrices. So that's just the additive group of real numbers. And it's SO. I guess this is actually a direct, but it's not a direct product of groups, so I'll just write it like this. SO2R. Well, that's just a one-dimensional torus. And that is not simply connected. It has fundamental group. I1 the additive group of integers. And in particular is not simply connected. In other words, there's covering groups. There's covering groups of this real group. And so just a little bit longer. I think I haven't read enough on this. I was preparing other things, but it's my understanding that this phenomenon also works for p-adic groups, for p-adic SL2. Okay, so a similar phenomena. Apply to the p-adic groups. It's a different calculation altogether. G2P SL2QP. I'm going to say, I think, I read this, but I've sort of read so many things lately that I think so what we can do is, let's say, so those would also have topological, not algebraic, but topological covering groups. So let G tilde A be a product over P of G tilde, product over V of G tilde QV be a finite. So you could do a finite covering, let's say at finitely many places, a finite topological covering group. So let that be a finite topological covering group of GA. And then consider the regular representation of G tilde A on, well, it's going to be its covering group, so we'll take the regular representation of GA on L2 of, can't do anything with GQ, that's fixed. But G, there's no, we don't want to consider the topology of that, it's discrete. But these other groups have topologies. So I'm taking a slightly bigger group here, and I'm taking the regular representation of this slightly bigger group by right translation on this. That's a huge subject. It is a huge subject, which largely undeveloped. Wide open. And it includes, you have perhaps studied metaplectic groups. I'm going to just write, and I'm going to write with bad notation. I didn't think about this, but the metaplectic group is a twofold cover, but I think it's, I guess, a topological cover, twofold cover of SL2. There's also the representation of the metaplectic group on 2n, a metaplectic cover of SP2n. And much more generally, these things have been studied, and a large there are many, many of these things, and a large collection of them have been studied, their properties studied, by Brzezinski and Deligne. Deligne coverings. These are, let's call them BD coverings. Brzezinski, Deligne, BD, Brzezinski, Deligne coverings. And as I say, it's a wide open field. It is expected to everything that you can do with GA over GQ and automorphic representations, it's expected you can do with this and get yourself many more examples. there are no doubt relations between this and automorphic representations in the traditional sense, but there are many more representations of these covering groups. And I'm going to just say, hope don't make us all late for our dinners, but let's just say that this is a wide open subject. There's one of the people that writes very well is Wietek Gam. And so see Wietek Gam, and I guess a graduate student of his, Fan Gao. The Langlands Weissman. They call it it's a very nice paper, quite long, but they could just consider an introduction, a preliminary introduction to what is a huge undeveloped field, and they call it the Langlands Weissman. Program. So the name of the paper is the Langlands Weissman Program for the Belinsky Deline extensions. Weissman, I guess he's written a lot of papers on just the structure of this. Well, his contribution seems to have been a construction of what should be the dual group, the L group. What should be the L group of one of these things? And he says it's often the same as the L group for G, but often without a canonical splitting, which is what the L group of G has. And it is also, in other situations, a torsor, where you have a simply connected group, dual group. A torsor is so a simply connected L group, let's say with values in the A group. Well, if you'll recall, that's exactly what we had for the construction of, it's that object that we had it for the construction, the explicit construction of the global G group, GF. So this is actually, I kind of hid my construction in 2000 and wasn't really noticed, which is good because I want to be able to think about it now. No, don't quote me on that. But I mean, these guys hadn't read it, but it's promising. It looks like they are defining L groups in a slightly broader context, which seems to match what we put for the construction of the group GF. No, I'm sorry. We're just talking about LF now. So it seems very promising. I think there's a lot of there are other indications that this somehow that these things have to lead to an algebraic group, which would be related to periods, exponential periods. So I will try to say a little more about this next week in 2 lectures. It's dependent on me being able to read enough of it to say something concrete. But in any case, this is wide open, and everything we've done with the Langlands program and algebraic groups can and should be done, we assume, for these groups. That includes automorphic representations. These guys talk about exponential automorphic representations. They define them. They should have functional equation, analytic continuation. There should be a principle of functoriality. There should even be a theory of endoscopy. That, in short, everything that's done for Langlands, for automorphic representations in the Langlands program, presumably should be done in this. There are perhaps some progress in it. I'll mention this next time. There, in the case of the metaplectic group, which is a very special case of this, Wenwei Li has established the trace formula, and he has stabilized the trace formula, which is a big step. And he has stabilized the trace formula. He hasn't proved endoscopic identities and packets, but he has stabilized the trace formula in that special cover, in particular covering, and it's on the web. You find this paper on the web, pretty long, but questions, comments?